We'll be recording this session as usual. And can someone tell me what do we use for describing or doing the lexical analysis? Can someone tell me what do we use? What do we use for describing the syntax? Not the concrete, but the lexical part of the language. What do we do? What do we use? Anybody? Do you hear me? Can anybody respond? Someone please respond if you hear me. Maybe I am not.
Duyuyoruz hocam.
Okay, so then you must have heard my question as well. So the question was, again, what do we use for describing or in the lecture? In a lecture, we defined the symbols that we use to actually use in that language, right? So what do we use? What type of, let's say, formalism or tools do we use to define the syntax, lexical syntax? Yes, in general, we will be defining a grammar, but what is that specifically? What type of a grammar is it?
Regular expressions, maybe.
Okay, so that's, yeah, regular expression is used for that. Good. From grammar's perspective, so regular expression is a kind of a is a subset of a grammar that we discussed, and if you recall the hierarchy, there were a few things like regular grammars, right, and then context-free grammars and so forth. And regular expression is some sort of an implementation or a kind of a description or some form of a regular grammar. And can anybody tell me what a regular grammar is? How do we define a regular grammar? Someone? Anybody? Operators? You have to be more specific than that. So if you recall, we said a grammar is a meta language, right? And in a specific form of this let's say meta language, or this meta language can be actually specified through 4 things. We call this BNF. And those things were, one, we would define the non-terminal symbols, first of all, terminal symbols that we'll be using in that language, or in that, exactly that language or in that grammar. The second one was non-terminal symbols. These were like things that can be substituted with a combination of terminal and non-terminal symbols. And the substitution would be done by the third thing that we would require in this BNF, that is the rules, the production rules that will take a specific non-terminal symbol and put it in, or replace it with, let's say, a set of perhaps terminal symbols. And then we'll have a start state that you would say, okay, start a symbol, a non-terminal symbol. You will say, okay, my language, the grammar that I'm describing, or the language that that I have, will start with, the description will start with this symbol. And what we'll do today is we said there were a few of these. So there are, we have seen one form of this grammar, this regular um, um, grammars, and specifically they had a regular grammar had two forms. One is it could be either a left regular or right regular, and we had specific limitations in the BNF that specifically specific limitations on the form of the production rules. We said the production rules can be either something like this: a non-terminal symbol can go to either another symbol, a non-terminal symbol, and some, let's call this with a small omega, some other terminal symbols, or the other way around, this way. And there will be no other, and perhaps as a non-terminal symbol in a production rule can go to an empty list, empty thing, or to a set of terminal symbols. If this is actually followed by or this is what you have in your production rules, we call this a regular. This one is a left regular, and this one is a right regular grammar. All right. Now what we are going to do is we are going to look for a little bit more powerful form of these grammars. So these are very restricted grammars, this left regular or right regular. And we said that they can be used to define the lexical syntax of the programming language. And a specific form of that was regular expressions. And implementation-wise, regular expressions can be implemented as deterministic finite automaton. Okay, in a deterministic finite automaton, DFA. Now we are going to go for a little bit more expressive forms of grammars. We'll call these context-free grammars. And these are going to be used to actually describe the concrete syntax, the rules where symbols come together. Like what will be the syntax? Let's say you can define such a thing or use such a thing to define, for example, let's say a for loop in C, or let's say a if statement in C or some other language. So, and again, this is going to be done with using BNF notation. And here, the production rules will be a non-terminal symbol A can be actually can go to or can produce a string of terminal and non-terminal symbols, and there is no limitations, specifically the order of these terminal and non-terminal symbols in this W is not limited. When that is the case, you have these context-free grammars. If you had some sort of order or some sort of limitation in this W, like I have above, let's say a single non-terminal in that omega or W, just a single one on the either the leftmost or the rightmost one, then you have these regular grammars. And now we are going beyond these regular grammars to have more expressive power, perhaps to do certain things that regular grammars cannot do. Okay, so this is gonna be a tool to define this concrete syntax, but we also need a way to actually implement this concrete syntax. So I need an implementation, some sort of an implementation or a way to implement, given, let's say, some grammar in BNF form, can I hope to actually have an implementation that can actually give me the meaning or implement the meaning of that syntax, whatever that is. And this is going to be done by using a parsing method. We'll call this parse trees. So these are going to be some sort of a graphical representation of a derivation. I haven't defined what a derivation is yet. We'll do so in a few minutes. But there will be some sort of these parse trees can be used to is actually a graphical representation of derivation where each internal node, the left hand side of a production rule, is a node in the tree, or defines a kind of a production rule from root to the child, or from that node to its leaves or its branches. And parse tree in this particular case will have children nodes, child nodes, right? They will be the right hand side of production rule. The leaf that we'll have at the end, they will correspond to terminal symbols. These are the tokens that comes from the tokenizational lecture out of the lecture, or it can be also empty. So let's see what we discussed is regular grammars, and context-free grammar is actually can in principle be is a set of recursive production rules used to generate a set of patterns of strings, right? So they consist of set of terminal symbols. We discussed this, non-terminal symbols and production rules and the start symbol. Okay, and we'll be using these to generate a terminal symbols from a CFG, a set of terminal symbols. So what we do is we begin with a string. This is the derivation or building the parse tree. We begin with a string consisting of the start symbol. This will be a part of the, so this will be the root of the tree. And we'll apply one of the production rules that has that start symbol on the left hand side. There is something here that I have left hand side here, but it should be left hand side. Replacing the start symbol with the right hand side of the production. And repeat this process of selecting non-terminal symbols in the string and replacing them with the right hand side of that production corresponding production rule until all non-terminals, we have all the non-terminals have been replaced by terminal symbols, meaning we have leaves that have the leaf nodes will have only terminal symbols. This will be a derivation, and they will be used to kind of check, in this case, the syntactic correctness of a given language. So the lexical analysis will result in a stream of tokens. The parser will actually have these tokens, and this is the syntactic analysis. We'll take these tokens and say if the given language, if the given instance of that language if that is indeed a valid instance of that language or not. So this will be the parser, simply syntax parser, you can call it. We call this lexical analysis, lexical parser. And usually lexical analysis is called lexical analysis or tokenization or whatever. And this syntactic analysis is actually called parsers. And if we have a unique parse tree for each language construct, so we need to have a unique parse tree for each language instance of that thing. And then a program will be a collection of parse trees rooted at the top by a special start symbol and so forth. And then parsers can be hopefully automatically built from BNF describing the language. So now what we are doing is we are saying, as we did before with, for example, I use a regular expression to describe let's say a variable naming convention or identifier naming convention of my language. Now what I'm doing here is I'm going to be actually describing my syntax of my language. When we say syntax, we mean, okay, I want to be able to say how do I construct an if statement or a while statement or an assignment or whatever, right? And then if I have the BNF as a not regular, as a context-free grammar that describes this syntax of my intended language, then parsers hopefully can be built out of this BNF automatically, hopefully. If it is done, then I'm in good shape, because what I'm doing is I'm just describing my language grammar using or my language, the syntax of my language using a grammar. And this grammar can be used to actually generate code that can do parsing. If this is available to me, this is a very, very powerful tool. Now, of course, this automatic conversion should be possible, and we are going to see that this is not possible for every CFG that you have, every instance of a, let's say, context-free grammar, right? So that means that ideally you want to have an automatic programming capability. You define the BNF, and then someone actually gives you the code. An algorithm builds you the code to actually parse any tokenized string or input that you have, and tells you if you have a syntax problem with that thing based on the BNF that you provided. So if this is the case, this is very powerful, but we'll see if this is the case for anything that can be written as using context-free grammars. And there are tools that actually does exactly, there are tools that actually do this thing exactly as we defined here. So these tools, given a BNF, of course, there will be some way of defining this BNF. We are going to see that. They can actually generate a C code or C++ code, or maybe Java code, or maybe even Python code that can actually do this parsing for you. Meaning you give an input, it actually tells you if this input is a valid instance of your intended language. All right. So let's actually start with a simple thing. Let's define a CFG, even though we can do this with some other ways, like maybe using a regular expression. We are gonna see if we can actually define a simple thing. So my language actually is, or I wanna just write a grammar to describe floating point numbers, all floating point numbers, okay? So my language is floating point numbers, meaning any instance of a floating point number should be part of my language, should be And then none in anything else should be, let's say, should be flagged, or we should be able to detect and say that this is not an instance of my language. For example, if I have 1.0, yeah, this is a floating point number. 1.1 is a floating point number, whereas 1A2 is not a floating point number because there is no such definition. So now the question is, can we write a CFG, a context-free grammar, to describe the floating point numbers? Okay, so we need four things. One is we need a set of non-terminals, terminal symbols. What are the terminal symbols that are necessary for these floating point numbers, describing these floating point numbers? We can think of different ways, in different ways, but basically, I would say, or one way would be, think about digits and a point, right? So a proper floating point number, and not a scientific notation, but regular notation with a floating point notation, right? You would have digits from 0 to 9. Those are your 10 digits, and then a point. Perhaps if you are talking about signed numbers, we don't, let's say, forget about the signs. So these would be my terminal symbols. Anything else would not actually help me in defining a floating point number. Therefore, it will be useless. So now I decided what my terminal symbols are gonna be. My terminal symbols are gonna be digits from 0 to 9, 10 of them, and a point, right? So if I had signed numbers like negative and positive numbers, then I may need to add one more digit to the, or one more terminal to this, or two more terminals perhaps, plus and minus. If I go for a scientific notation, I may need to add other terminal symbols, but for the time being, I'm interested only with those digits and a point. Okay, these are my terminal numbers, the terminal symbols. Okay, now I need a set of non-terminal symbols, but these are probably related to the. It will be related to the production rules that I'm going to use, and then I will need a start symbol. So one instance of this one could be something like this, right? So think about a floating point number. Usually a floating point number has an integer part, as we can see here, an integer part here. This is the integer part, and then a fraction part merged or connected with a okay, this one connected with this guy here, right? So with a point. Okay, so I can say now a real number or a floating point number. I have it here, a real number, a floating point number. This is a way to actually describe a rule. I'm saying, okay, a real number, rule says left-hand side of a real number should be, this says should be or could be, maybe there are multiples of it, but at this moment I have only one. It is actually composed of an integer part, a point, character point, and a fraction part. Okay, as we said, this character point here was a terminal symbol. Okay, now fraction part is a non-terminal symbol because I don't know what a fraction part is right now. And an integer part is also a non-terminal symbol because I don't know what this is. This could be a lot of different things. Now, the integer part could be a digit, meaning I can have only one digit here. So for example, 1.5. So it could be just a digit. And then, or it could be a digit preceded by an integer part. So I have a recursive production rule here. This one says or. This means that I have two production rules for integer part here. One is integer part is a digit. The other one is integer part is a recursive definition, recursively defined as an integer part followed by a digit. All right. Fraction is similar, digit and digit followed by a fraction. I changed the orders here a little bit just to kind of show you that it could be either way. So these are the thing, and then digit is just simply either 0, a terminal character or terminal symbol, or 1, 2, 3, 4, 5 up to 9. These are all terminal symbols. So this guy here, this bar, these bars indicate that I have multiple rules here. This means that or digit is 0, or digit is 1, or digit is 2, or digit is 3, and so forth. Okay, so this is now what I have is I defined here what my let's do it this way. So I have, first of all my terminal symbols. This is a terminal symbol. This one, okay, this one, 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 this one. These are all terminal symbols. All right. And I also have non-terminal symbols. This is a non-terminal symbol. This is a non-terminal one. This is a non-terminal one. This is non-terminal. This is non-terminal. How many do I have? I have actually, I should count. Real number is 1. Integer part is 2, fraction part is 3, and digit is 4. I have 4 non-terminal symbols, okay? And I have bunch of production rules, which always goes like this. You have a left-hand side of a rule, which is a non-terminal symbol, and then right-hand side is a combination, concatenation, or a composition of terminal and non-terminal symbols in some way or another. All right. Okay. And we'll need, BNF asked us to have 4 things. We have now terminal symbols, non-terminal symbols. We have production rules. How many production rules do I have here? How many? Can someone tell me how many production rules I have? 2, okay. 1. Is anyone is asking to speak?
Is it 4?
Let's see. First rule is, let's look at this one. First rule is, it says real number is an integer part followed by a point and fraction part. So this is my first rule. So rule number 1. The second one is integer part says could be integer. Integer part is integer. This is number 2. It said also integer part could be integer followed by a digit. This is number 3. And then fraction says fraction can be either a digit. This is number 4. Or it is fraction is digit followed by a fraction. This is 5. Am I done yet? No, I have other rules. The 6th rule is digit is 0. 7th is, this is the 6th one. 7th is digit is 1. Digit is 2, and so forth. So 8, 9, 10, 11, 12, 13, 14, 15. I have 15 different rules here, production rules, for defining this floating point number. Language of floating point numbers. A language that actually tells or generates or checks or whatever, or defines these floating point numbers. All right, so 15 of them. There are 4 lines, you are right, but some of the lines have multiple production rules in them, separated by this or character here. This means or, it means that integer is either a digit or it is an integer followed by a digit. So this is integer part followed by a digit. These are two rules here. There are two rules in this one. All right, good. So now we also we have now 15 production rules. We need one more thing, a fourth thing. The fourth thing was we need a start symbol, which should be a non-terminal. So we need to specify our start symbol. In this case, most probably, you can see it, but I chose it to be this guy here. This is how I started writing this. I say, okay, I want to start with real numbers. How do I generate a real number from this thing, right? I have to define my rules, and then so that I can actually get to where I want to get. All right. Okay, good. So I have now those four things that is needed by BNF, this Backus-Naur form. All right. Now, perfect. Is this how is this useful? The usefulness of this is supposed to be that I may probably have an algorithm that looks at this thing, a program, an algorithm, a program hopefully, that looks at this thing, and you say, okay, once you say real number is your start point, and integer part, fraction part, and digit are your these are your non-terminals, and 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, these are your terminal symbols, then that program is gonna generate an output, another program that can take a stream of tokens, which will be, in this case, these terminal symbols, digits from 0 to 9 and 1 and point, and then it will tell me if that particular string of tokens is indeed a floating point number or not. And it should be able to say, okay, no or yes. Okay, so this is the aim here. If I have this one, this is perfect. Now, this tool would be very useful. I just need to actually understand how to write this thing for my intended language. And once I understand it, I write it, and then programming is done already. So this is a very powerful tool if it works. But we are going to see that even in this case, it is a little bit difficult, or at least automating it would be quite difficult. And let's understand where that difficulty comes from. All right. So we already talked about this. So this is a simple parse tree, a sample parse tree for an input like this, 3.14. All right. So how did this happen? Okay. Assume that someone gave you a text. The text was just this, 3.14. Now you had a lecture. You should have a lecture or tokenizer. This is a string of input in a file or in a text or whatever, in a string variable, right? And I need the tokenization of this one. How do I tokenize this one? The tokenization said I need tokens are this guy and the digits. So then I will have these tokens. I have 3 as a token. This tokenization in this case is very simple. I just take I just split the character into split the string into characters. One is 3, the other one is point, the third one is 1, and the fifth one is 4, or fourth one. Is it fourth one? Fourth one is 4. Okay, so these are my tokens. 1 token, 2 token, 3, third token, 4th token. I have 4 tokens. Perfect. Now, what I want to do is, given this particular grammar here, this context-free grammar here, I want to ask the question: is this really part of this language? How can I do that? I can do it this, let's say, one way. I will start from, say, okay, where is my start symbol? Real number. I have only one start symbol. Okay, I start with this one. In this case, this is easy. Sometimes you may have one start symbol. You'll have one start symbol always, but sometimes you may have multiple rules that actually has the start symbol on the left hand side. Okay, but here these are my rules and 15 of them. We counted 15 or 14, I don't remember exactly. Let's call it 15. And the real number only happens or only is actually occurs just once on the left hand side of this rule. Okay, so this must be the rule that I need to apply. So I apply this rule. It says now that when I apply this rule, what I need to see is my input should have a point somewhere in the middle, and I should have an integer part on the left of this and a fraction part on the right of this thing. All right, fine. I'm not done yet. I cannot call this as a parse tree yet because I need all the leaf nodes should be all terminal symbols. Right now it is not terminal symbol. It has one terminal symbol here, this guy, but this one and this one is not terminal yet. So these are non-terminal. How do I go from there? Let's say that take the integer part on the right. I can look at this guy here. If this symbol here, this symbol, this is I'm just kind of doing this heuristically. I am not actually building an algorithm yet. I'm looking at this symbol here, this terminal symbol. Do I have that in my input? Yes, I do have it in my input. So this is actually, this has one left-hand side and one right-hand side of it, or not left-hand side, but something preceding it and something is actually following it, right? So can I actually take this part and generate this part through this path? Yeah, I can. I can do integer goes to digit and digit goes to 3. I'm done for the left hand side of this point here. Can I do the same thing for this one? But this time I need to generate a subtree that will actually have 1 and 4 on its leaves. Okay, so I start with fraction. I need to actually go for fraction. I cannot go just digit because this will be only one leaf. I need 2 leaves. I need 2 leaves here. One is, I say fraction goes to then it must be this guy that I need to use, integer and digit. Integer part, oh sorry, I'm looking at this guy here. Digit and fraction, digit part and fraction part. Digit part can go to 1 and fraction part can go to digit and then it can go to 4. Okay, so as a person, not an algorithm, but a person, I have an algorithm in my mind as well. I can actually look at this one. I can build this parse tree for this given input. All right, perfect. I can do this one. So this is a sample parse tree that would actually generate or that will explain this input sequence 3.14. So this means that since I have a parse tree, I'm okay. This means that this is an instance of this language. If I didn't have a parse tree, then I will say, okay, no, there is no instance of this parse tree. This is not an instance of this this is not an instance of this language that this grammar is explaining. Right. So if I have an parse tree, this means that I am able to generate that sequence of tokens using the rules of this grammar that this grammar defines. Therefore, that instance is part of my language. If not, then I'm done. If I'm not able to find such a parse tree, then I'm done. I say that if I'm not able to find a parse tree like that, that means that this is not part of my language. Now, of course, doing this by hand is not interesting, right? We need to program this. And then we need to do more things after programming this one, of course, but we'll come to that part. So, good. So let's look at another one, another example. What I'm going to do is I'm going to define a program, very simple programming language, sorry, that will actually be following like Algol style or Pascal style thinking or grammar, syntax. So a program is starting with begin word keyword begin, and then it has some statement lists, and then it has an end. So this is a procedural language like Pascal or Algol or the style is quite similar to Pascal. So this is a program, but I don't want to just define. I want to define a little bit more of these things here. So this is written by someone, by me. A program actually is my probably start symbol. This is my non-terminal symbol start. It has a terminal begin. It has a something in the middle and an end. This says that I will have a begin keyword, an end keyword, and something in between. Not just one thing, hopefully. That's why I call it list here. Something in between, okay? What is a statement list? A statement list is actually can be a statement followed by a semicolon and another statement list. All right, good. So this is probably this recursion, you can already see that it will never end. Therefore, it has to end somewhere. Perhaps you can write another one that actually statement list can be empty. All right, perhaps. Then a statement is, in this case, I'm going to have a simple language, a very, very simplified version of Pascal, for example. The statement list statement can be only, a statement can only be an assignment statement. And it will be actually, a statement is an assignment statement. How do I know it's assignment? Most probably I have an, because I have this thing here, this equality sign, and then a variable on the left and an expression on the right. A variable can be only, in this particular case, I say my variables are A, B, C. I don't have any other variables. So as I said, this is a very, 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 very restricted language, a simple language, very, very simple language. It has only 3 names in it. These are the things A, B, C. And an expression can be 3 things. It can be either just a single variable, and it can be a variable minus variable, or it can be a variable minus variable plus variable. And as you can see, there are no literals here. Perhaps I should have added literals like numbers, but I don't care about them for this language. So the question is, this is as I said, this is not a language actually. You cannot consider this as a language, but why not? I call this a language because I have a grammar that I define the syntax of this particular language. All right. So let's say that I have now what I want to do is I want to actually see what I can derive with this one. How do I derive? What is the, let's say, the things that I can actually write with this grammar? What type of sequences of tokens, terminals that I can write here that can be part of this language? So for that, I will start with my begin symbol, right, or the start symbol, which is program. And program appears only once on any rules left hand side. Therefore, I have a unique choice there. I can only start with this particular rule here, nothing else. All right. So I say here, program is, I usually say goes to here, or implies, or produces. You can say anything, but I usually say goes to. So program goes to begin, a keyword, a token, a terminal symbol, a statement list, a non-terminal symbol, and another keyword or a token or a terminal symbol. Okay. Now this is very good. I know that these are up to this point. I have everything unique. Just one. I have one choice. I don't have multiple choices. Now here I know that my input sequence should have a begin and should have an end keyword, terminal symbols. And then I have some things in between. What are those things? Okay, let's look at this one. The statement seems to be here in this particular case only one thing. Statement goes to statement separated by a semicolon and a statement list. It's a recursive production rule. Statement is a statement or statement, sorry, statement list is a statement or statement, no, sorry, a statement list is a statement, semicolon, a statement list. Statement list is a statement, semicolon, statement list. You can see that this is a recursion here. Now, if you think about this as an algorithm, this is a production rule. It's like a simple algorithm. And you can already tell me that this recursive call will never terminate. You can already say that. Why? Because I don't have a baseline condition to actually terminate this. So I will have a statement and then a statement list. In turn, that statement list can be a statement and statement list, and then statement and statement list. So this would actually go forever. So I need, as I said in the beginning, this particular rule here is not sufficient, or it is not a good rule, because this will actually cause infinite recursions. So I need to have something in between. Then I will say, okay, statement list can be empty. All right. So now I have the statement list. I can actually do only one thing. Statement list. This stays the same. This stays the same here. I only replace the statement list now with statement, semicolon, statement list. All right. Now I have two options here. I have statement. This is a, these are, if you look at these things, there are two that are here, one here and another one here. These are two non-terminal symbols. This means that if I treat this as a parse tree, I will have this one. Program goes to like this, begin and end. And then this in turn actually goes to, so whatever, statement list. And this in turn goes to like this, statement, semicolon, statement list. Okay. Now, at this stage, this tree, parse tree, is not a final tree. Why? The leaf, the node, leaf nodes should be all terminal symbols. Are they all terminal symbols here? No. This is a terminal symbol. This is okay. This is a terminal symbol. This is a terminal symbol, but this guy and this guy, statement and statement list, they are not terminal symbols yet. So what do? I need to make them terminal symbols. So can I make a statement terminal symbol? Let's say if I pursue this guy here, can I make it a state terminal symbol somehow? Or can I actually have a tree, subtree, that can turn this into a state, at least the leaves would be terminal. Perhaps let's look at this one. Statement says var variable equal expression. Okay, let's go variable. This is variable equals an expression. All right. Is this right now a full tree in terms of the leaves should be all terminals? Not yet. Still, I have this guy here. This is not there yet. And this is not there yet. And this is not there yet. This is okay. Now, I need to continue further. I can continue in three different directions. I can either continue pursuing this, or pursuing this, or I can pursue this one. Which one? I don't know. Let's go from the left to right. All right. So perhaps I need now a decision here. And this decision, we have to be very, very careful with this decision, because we are going to see later on that this may actually, going from here, starting with the variable and pursuing the variable path here first, this all right. Do you hear me, guys?
Yes.
Okay. I think we had an electricity outage right now, and now it is back. Okay, fine. So if I actually go follow this this path here, this particular path, let's say if I go this way, or this way, or this way, I may end up with different trees. Okay, fine. As long as I get at the end a set of leaf nodes that actually they are all terminal, then I generate an instance of my language. Okay, but if I get two different trees, then I have to be careful. I'm going to come back to that one. So here, what it does is actually, so let's erase them all and let's look at what is happening here. So you see here is that it actually followed this one here. So it replaced that one with this guy here, and the rest is the same. Okay, what can I do? I can continue with, let's say, perhaps the same way. I can do one algorithm could be, if I'm able to actually choose anything, why don't I actually do it kind of systematically? Meaning, when I actually evaluate, when I have this one here, I evaluate the leftmost, in this case, the leftmost non-terminal, and I try to get rid of it. Or I can do a rightmost, or random. Randomness algorithmically is not a good thing usually. In this type of things, you want to have some sort of a, systematic thing, right? Random. Which random? Okay. Ahmed chooses the middle one. Ali chooses the right one, and the other one chooses the left one. That doesn't make any sense. So let's actually do one way. So leftmost, what I will do is each time I will actually look for the leftmost non-terminal symbol, and I'll try to get rid of it. Now you can see here, I come here, and then now in this case, I have two symbols, non-terminal symbols. I'm still gonna go with the leftmost one, this guy, and I will get expression goes to this one or this one or this one. Which would we choose? In this case, it seems to have chosen this one. I don't know why. Probably we are gonna see that this is not even looking at the input right now. It's just trying to generate some output. So then I can go with the leftmost one again, and then another leftmost one. This time the leftmost one is this guy here. And then I have this guy here, right? Leftmost one. Again, in this case, it went to the statement. So my guess is that, if this can go to the statement alone, we are missing here just something like this. It's not empty, but there is a second rule that statement list goes to either statement list followed by a semicolon and a statement. or just a statement alone. All right. So this one is a statement, and then the leftmost is still this guy here. And now I have this guy. Statement can go to var equal expression and so forth. Now, this type of derivation, I use a kind of a specific, deterministic, a systematic derivation. What did I do? I actually derived things by eliminating, at least try to eliminate or apply a production rule only on the leftmost non-terminal that I have. Now, we have a few different things here. In this, each step of this, any step of this derivation, like let's say this one or this one, is an intermediate step, and it is composed of the resulting sequence of terminal and non-terminal symbols are actually, they consist of, again, non-terminal, a sequence of non-terminal and terminal symbols. And we call each of these a sentential form. It's like a full sentence. Once we have actually the leaf nodes are actually reached, we'll have an instance of the language or a sentence of the language. This is coming from natural language processing. They call this a sentence. And here, what is in intermediary stuff, these things, they are not sentences, actual sentences, because they include non-terminal symbols. I cannot call them sentence. Therefore, what we call them is, in this particular case, as a sentential form. Okay, kind of an intermediate sentence. All right, this is important. We are going to come back to this one. Okay, now this type of derivation is just letting me kind of explore what possibilities I can actually have, what type of outputs I can generate with this given grammar. But our task was kind of different, right? We were trying to actually ask the question for the given instance, a given sentence. If I give you a sentence, let's say, if I say A plus B plus, let's say, C, is this an instance of this language? This is what we were asking. Now, we have to think about this and say, okay, how do we actually use these to explain or answer the question if this is an instance or not? So this probably is a way of doing that. But what this will do is, this will try to do kind of everything and then see if this is a part of that everything, it matches that everything. This will be probably very, very expensive. Usually the cardinality of this list of things that we can generate with this particular, even with this particular set or grammar is infinite, and you cannot just hope to generate an infinite set and then match a given set, a given instance of that in that infinite set. It is ridiculous. You wouldn't do that. You cannot compute it, right? Your program will not halt. So we have to find practical algorithms to actually do that. All right. So let's take a 10-minute break and we'll continue how to actually find those practical algorithms. We'll be resuming at 7 after 3 o'clock. Yes, my microphone is off because we are in a break. I'll be back in 4 minutes. Okay. Arada mikrofonumu kapattığınızdan falan bahsediyorsunuz. Ara verdiğimiz için mikrofonu kapattım. We'll be resuming in a minute. Yeah, right now actually. Okay, so let's look at another example following what we have. What we actually notice is that this the grammar with the derivation of coming from, let's say, or starting from a start symbol and moving to sentential forms using production rules one at a time is actually giving rise to some sort of a hierarchical syntactic structure, as you can see here in this example. And this means that actually it's a tree, and that tree has hierarchy, meaning you start from a high-level sentential form, and then you go at the end to an instance of that language. And somewhere in between, you have, let's say, you are getting closer and closer to the instance that you are seeking or you are trying to verify, from more abstract to more kind of an abstract syntax to a concrete instance of it. So let's look at the case where we have these set of rules here. These set of rules. There are quite a few of them. I have 1, 2, 3, 4, 5, 6, 7, 8 rules. And this is kind of expanding a little bit on top of that. No, this damn thing doesn't stop. Let me just get rid of this thing. All right. Okay, so this is kind of a little bit more extension on the example that we have seen a few minutes ago, where I am looking for the assignment statement, ID equals expression. ID can be ABC, and I'm working on a little bit more on expressions here. I have expression can be either an ID plus expression, or ID times an expression, or within a parentheses expression, or an ID, right? So in this case, can I actually show that A equals A assigned or B times C in parentheses A plus B times C within parentheses A plus C is assigned to A? Is this an instance of this language? We can easily see that by starting from the start symbol, which is the assign in this case. We have only one option, so we enumerate that, or we evaluate, or we produce that, and then we go from, in this case, from left to right. We go for ID. Can I go to ID and do something? In order to get this one, you can easily see that. In order to get to this one, now my left-hand side, the most left terminal item is going to be an A, right? So if I generate, let's say, if I use A, ID goes to B, I could have done that. I could have actually done this one, but it will not match my input. So by checking the input, I can say, hey, I don't need to actually worry about this guy and this guy, because they are not going to be useful. If I actually generate them, they are not going to be useful in my question, or in answering this question. Is this part of your language? So you can see that already these production rules that I need to do, you apply, should not be just chosen at random, because especially if they lead to infinite sets, then I have to be very, very careful, because I cannot actually hope to go through those infinite sets. So in that case, what I will do is I will actually say, okay, here I can already say B and C is not useful, because A is the leftmost child, or the leaf that I have, right? So that's why I go for A. And then what we can do is we can see it already that the second will be this one. This is ID goes to A. And then I have only expression left here in this sentential form. Expression can be either of these four. It cannot be this one, because if it is this one, it won't be able to explain this entire thing here, right? So I know that there is either a multiplication or a plus sign in it. So I need to choose something that from the left-hand side, I can try to choose something that actually matches that. So seems to be that, okay, maybe I choose multiplication. And then here I choose the multiplication, ID times multiplication, and this is explaining it. ID times multiplication, right? So I can see that if let's look at this again. I'm here. I'm trying to actually replace ID with something. All right. Sorry, I'm here. I'm trying to replace an expression with something. I have four options. I can either go for this one, or go for this one, or go for this one, or this one. So it's easy to see that if I go for this one, it will actually just go to ID, and I need to choose one of those things, and I'm not going to be able to actually process the rest of the things here. I won't go for this one because it requires a terminal symbol on the left-hand side, and left and the right, most terminal symbols, they are actually parentheses, and I don't have a leftmost parenthesis here. I do have a rightmost parenthesis, but not the leftmost parenthesis, so this is not going to be useful. I can go for ID plus expression or ID times expression, right? So I can go either way. But if I try to go ID plus expression, let's look at that one. So again, I'm here. If I choose ID plus expression, I can easily say that if I say ID plus expression here, so this is A equals ID plus expression, right, for this one. Now, I need to go for ID, and ID has to be one of these ABCs, right? If I make it, if I have to make it A, sorry, B, because B is here. Now, if I make this B, I have B plus expression, and whatever I do here, I cannot actually reduce this to this guy here. So this will be a path that is actually not useful. But you can see all of the kind of the difficulty in this. So the question is, how far do you need to go to know that actually you cannot do that anymore, right? So if I have any type of expression here or any type of production rule, this could be quite difficult to actually do. This is a kind of a simplified expression, simplified thing. I could have actually gone something like this: expression goes to expression plus expression. This would have made it much more difficult. So many paths to actually check and make sure that it is actually it goes there or not. Now you can already see that depending on what the grammar is allowing me to do with the production rules, my algorithm to check a given input's validity or for the question, is this a part of the language or not, it becomes more and more difficult. It can be actually extremely difficult to make this a simple algorithm or even a decent algorithm, right? So you can already see the difficulty. But our point here is that, first of all, each of these things, even let's say in this particular case, in this with this grammar or context-free grammar that we have here, each of these states or sentential forms actually describes some sort of an intermediate hierarchy. And as I go down more and more, I am actually getting closer and closer to an instance of it. And this is what we call what we actually hope a parse tree would do. Therefore, this is when we talk about a parse tree, it shows us these, let's say, these levels. You see in this level, you have the start symbol. In this level, you have the first sentential form, and the second sentential form, and the third sentential form, and so forth. And as you go lower and lower, at the end, you are going to have an instance of this thing, an entire, an instance of sequence of things that are composed of only the non-terminal symbols. You can see here, now these are all non-terminal symbols. How do I know that? Because I have A here, and then B, and then I will go, sorry. So this is A equals B star parentheses A plus and C close parentheses. This is the parse tree. Of course, in order to show this a little bit better, what I could do is, I could have actually pushed this one at this level here till the end. So this is A, I could have pushed this one to B, and I could have pushed this one to here equal, and this one to here star, this one to here A, no, sorry, this one to here this, open parentheses, this one here A, and this one here plus, and this one here C, and then this one here as close parentheses. So this is the final output that I'm actually looking for. And in this case, this is explaining this. So if I were to ask the question, let's say that if this was, let's say, D here, not B, of course, I wanted to say, and let's call this X. If this is X, right? So would this actually parse tree? Am I able to create a parse tree for this one? Okay. Nothing is gonna change till, let's say, I have everything. So everything up to here is gonna be the same. So everything up to here is gonna be the same. Actually, even everything up to here is gonna be the same, right? So expression goes ID. Now, in this one, there is no ID goes to X. This is X. Since there is no ID goes to X here, therefore, I cannot actually do this one. Now, so this means that I cannot actually generate a parse tree for this particular instance. Does it mean that the question is going to be, does it mean that I can never generate a parse tree? Did I actually explore everything? So if you are sure that you explored everything and you cannot explain it, then perhaps your answer is, then you say, okay, no, I cannot actually instantiate this because there is no parse tree for this particular thing. So your algorithm needs to be able to guarantee that. Now, the basic, or let's say, is there an algorithm given a context-free grammar? Is there an algorithm that can actually terminate within an or that will halt at some point with the right answer? Is it depends on the first thing that it's going to be that it depends on the what you have, what type of, let's say, production rules you have. So any generic set of context-free grammar might be, so we might not have an answer to this one. We are going to talk about this one. So it will depend on what set of rules you have and what they can generate and what I can actually match, how I can match that. So the question is going to be for some simple rules, like for example, if it was the context-free grammar is a regular grammar, then we are going to see that this is already doable because we have done it. We said regular expressions can be actually done as a deterministic finite automaton. That means that we can actually write an algorithm to solve it. It's guaranteed. You don't need to worry about it. There is a algorithm that actually can take a regular expression and solve it. So this means that for those type of cases where you have your production rules follow a regular grammar, then you can do that. But we know that regular grammars are not going to be expressive enough. So where do we know, or when do we know, or for which type of context-free grammars do I have an answer, and for which I don't have an answer? We have to talk about that in detail now. So a parser, this parse tree, once we talk about actually generating a parse tree, now let's talk about algorithms to do this one. I can do this by hand, manually, because I have hopefully an evolved brain that I can actually do these type of things. Not necessarily always. For a complex thing, I may not be able to do, but for these simple examples, it's easy to do. Now, the question is, for a complex example, what do we do? For anything, can I actually do a parser? So the parser will determine if the input program, the series of tokens or sequence of tokens, is syntactically correct. If I have, this is what the parser is doing. This means that If it is correct, then it will generate a parse tree. This produces a parse tree for the correct input program, and it will actually return errors if it is not able to actually find this parse tree, meaning it's not syntactically correct, the input. There are two ways so when you think about an algorithm like this, you can approach this in two probably basic ways. One is you can try to solve it top to bottom, top-down approach, meaning you can start with your symbols, start symbol, and try to generate the output that is matching your input. Now, you cannot do this blindly or just, let's say, without any restrictions, because just starting from a start symbol is going to cost you maybe it's sometimes infinite amount of time to actually generate all these lists, all these instances, and then match them. So you have to constrain that search somehow. And we are going to talk about some algorithms that actually constrains that search, meaning I won't want to actually go top down from starting a start symbol and, okay, try everything. I shouldn't be trying everything. I should be trying only a finite number of things so that my algorithm can in time tell me, hey, you are syntactically correct, the input is syntactically correct or not. And then it should be able to actually generate the output. If it is not, then my parser doesn't do its job. It's impossible. I cannot wait forever for my program to compile, at least for the part, this concrete syntax part. So if it is taking 10 hours, 20 hours, it's not useful to me. This is one part, the top-down approach. The other approach could be actually from bottom-up, meaning I look at the input sequence of stream of tokens or sequence of tokens, and try to go in that hierarchy further up and up and up till I reach a start symbol. I can go either from start symbol to the leaves, getting their answer, or from the leaf, each leaf or the combined leaves or the leaf nodes to the top of the tree to start to reach the start symbol. So these are the two main approaches, and we are gonna see that actually they're not necessarily easy algorithms, and they are not gonna work for every input or for every grammars or every grammar that we can actually, or and every context or any context-free grammar cannot be, let's say, verified with this top-down or bottom-up approach. But what you need is you need an algorithm, automated algorithm, given your BNF, your production rules, should be able to actually convert to a code that will answer in finite amount of time. So this is our next question that we are going to ask. This top-down approach is also called recursive descent parsing. It's recursive because every time you are trying to actually get rid of one of the terminal symbols. It's top-down because you are starting from the start symbol. When you look at the tree, the parse tree, it's like going from top of the tree to the bottom of the tree. That's why it is called top-down. Again, recursive, because again, it's descent, it is descending, going down. And recursive, each time you're actually eliminating one of the, let's say, terminal symbols, hopefully, non-terminal symbols with hopefully terminal symbols, hopefully, but it's not going to be possible, but at least in time, you'll be reducing them. So this is called recursive descent parsing. What this is actually doing is, this is indeed a depth first search algorithm for the of the derivation tree. Okay, why is it depth first? What you are doing is you can explore this one first, all the possibilities, right? So This means that you want to actually when you try to get let's say the example that we had, maybe the earlier example, let's say here. So what you are doing is you wanna, when you are here at this level, you want to actually get to the bottom of one of these things, either of these two. This is already terminal, this is fine. And then you will actually explore this and then finish it. And then you'll finish it. You can see that this is depth first. You are going depth, and then once you actually reach the location or reach the leaves, then you go back and actually do the other one. All right, so this is depth first search of the parse tree. There is an example, a simple example here. You have a production rule. Expression is an x terminal plus t non-terminal. T is within the parentheses expression. You see that this is actually quite recursive. T, E goes to T, T goes to E. So there is a recursion here. We have to be careful. And T goes to X. If you are given something like this, this is the way that you would actually do a recursive descent parsing on this one is you start with here with start symbol, and you have only one possibility here. And in this case, now you need to go for this guy. Now, for this particular algorithm, you can already see that, or let's say particular, not algorithm, but particular rules that you have here, the production rules. The right-hand side of each rule has only one terminal, non-terminal symbol. So what you are doing is you are taking a non-terminal symbol from the left-hand side and then reducing it, or actually replacing it with a right-hand side, which has only one terminal, non-terminal symbol. So this means that every time you actually go to, when you are doing the depth first, what you are doing is you have only one depth to actually, one branch to follow, not a multiple branches. You don't have 10 branches to follow as was the other case, right? Here, you have only one branch to follow. Now, this type of algorithms, in this case, when you have only one branch to follow, it is easy to answer the question, which branch? I want to do depth first, but which depth? Which depth am I going to go for, right? So if you have only one branch, you are going to go to that depth. But if you had two, so for example, if I had here, T goes to, I don't know, let's say T goes to A and B, like this, A and B meaning means they mean here terminals, non-terminal symbols. Then at some point in your derivation or in your parse tree, you are going to have two branches to follow. Now the question is going to be, which branch do I follow first? The left one or the right one? A or B? Now you can say, okay, I'm going to always go for A, meaning the left one, or always going to go for B. But then the question is going to actually do this follow A or B, do I do the same thing at the end? Do I get the same thing? So this is the other question that we need to ask. Now, we also said that we don't want to actually do this without looking at the input. If I do this by just looking at the production rules, I can end up with an infinite set. I need to somehow check when to actually, or how to constrain this search with the input, because input is my guide, right? Input is, if the input has something in it, and my choice, the choice, in this case, I don't have a choice because the only choice I have it is actually here. Now, if I have a, let's say, multiple choices, which path to follow and when to actually say no to that path or to that exploration needs to actually somehow, I need to match things with the input, right? And this is not an easy thing to do. It's not, you cannot say that, okay, you know, I'm going to check the input and I'm going to just every step I'm going to come to, let's say here, let's do it this way. You cannot just say, okay, at this stage, let's say if I am at this stage here, let's say here, how do you check actually as partial form that x plus, so this partial form is x plus parentheses expression, close parentheses, that's it, right? This is it. How do I check this with my input? My input was this, right? How do I check it? Perhaps one way to do would be if I have, let's say I look at this from the left to right. I look at the leftmost of this guy and leftmost of my input. And I say, okay, hey, if my rules are actually, let's say at some stage, this could have been also the rightmost, but anyway, in this case, it's the leftmost. At some stage, if I don't have anything on any non-terminal symbol on my left and any no non-terminal symbol on my right, then I can actually check all the terminal symbols from left to right or right to left till I get my non-terminals, right? This is I can do. And I can say, okay, hey, no, it cannot happen. So in this case, for example, I need to have x plus parentheses. And I know that x plus parentheses is here. And then here on the right side, I have to have a parentheses. So for this one, it is easy to say, but is such an algorithm practical for any type of production rule that you have? And the answer to that is we are not going to get into the details of the theory behind this. The answer is that no, not everything actually can be done easily. So there are a subset of grammars that these context-free grammars that can be solved using this recursive descent algorithm. By first, algorithm is actually recursive descent coded directly from the BNF, the rules. There is a parsing table that actually will not implement these BNF rules. There are two versions, recursive descent and parsing table version of these. They both use what we call an LL algorithm. The LL algorithm is, they work on same subset of all context-free grammars. The first L refers to the left to right scan of the input. So it said, okay, what I cannot actually just say, look at the left, look at the right, and then do this. If it is not doing it, go back one step back, and then re-evaluate it and go down and so forth. This is not an algorithm. This is just a wish, right? So there has to be some deterministic algorithm. The deterministic part of this algorithm, or this algorithm, is a simplest version of what we described. And we say, okay, what we do is we always look at the leftmost input first. So when we do this input, when we do the input, let's say x plus x, we start from left to right, the left to right scan of the input. All right. Now, the left to right scan of the input means that I can look at any given time one part of the input, and I can actually move one at a time, maybe two at a time. There will be this look ahead stuff later on. We are going to see that. So I'm going to be actually be consuming my input. And when I consume some of my input and I say, okay, I know that this is actually already guaranteed. When I do a leftmost, so if I do in my tree, let's say in my parse tree, if I go for leftmost derivation, meaning if I do depth first from the leftmost side, I can hope to actually match this guy with my input from left to right. So the first L here refers to left to right scan of the input, and second L refers to leftmost derivation. That is the leftmost derivation is actually used, meaning I do a depth first search on the leftmost branch if I am able to. So this means that I'm gonna be actually deriving or using a production rule on the leftmost non-terminal in my sentential form. So this is this. So this algorithm says if you do left to right scan and you do actually do a leftmost derivation in your derivation, then this set of algorithms or this algorithm is able to actually work on a subset of CFGs, context-free grammars. Not all of them. They cannot actually work on all of them. They cannot actually generate answer or answer for every type of CFG here. So it can only work on a subset. Now, what is this subset? Are we going to talk about these limitations of this subset? Probably a little bit. This is out of scope of this course. But this algorithm is able to actually work on some subset of CFGs. And there are two implementations of them. One of them is actually recursive descent. One is the parsing table method. Okay. There is also another part, another possibility. These are called LR parsing. The other one was LL. So LL is top to bottom. Okay. Why? I do top to bottom derivation of the tree, and I go for the leftmost. And then since I go to leftmost, so my derivation tree and my input here, I go for the leftmost, meaning I go from here to here this way. Therefore, I go from here to here. So I will instantiate this one first here, and I'm able to match that with my input. The second one with my second input, the third one, the third input, and so forth. This is the LL algorithm. Okay. The LR algorithm, on the other hand, this is a kind of, you can already see that this is going to be left to right scan, but the rightmost derivation. So this is actually corresponding to bottom-up parsing. So left to right scan of the input again, the same way. But this time what we are doing is we are reversing this order here. We are reversing this one, and we are actually trying to get from bottom up, meaning we actually, again, we need to match these. The way that you need to actually do this one is you need to actually make sure that the rightmost derivation is generated. So in your production rule, when you go one up, you would actually get, you will actually try to instantiate the rightmost part of your sentential form. Now, we are going to come back to this one in a few minutes again, but these are the two main algorithms. Again, they're not going to work on all sorts of CFGs. It's going to work on, and you can already see why, especially if you have multiple options when at a given level, both for the LL and for the LR algorithms, then you need to make decisions. And those decisions cannot be easily made by looking at, let's say, left or right scan of input. You need to actually do more elaborate things in that case. Okay, so now this is let me see. Now, we are going to talk about, so one of the things, we are going to come back to this algorithm again. I'm going to discuss a little bit, especially this LR algorithm and specifically shift-reduced parsers. But before that, we need to actually kind of clarify one thing. This, the CFG, a given CFG, can be actually interpreted or can be given CFG for a given input, for example, can be derived, it can actually result in multiple derivation trees or parse trees. So there is an example here. You have expression goes to expression plus expression, expression times expression, A and B, C. This is very similar to what we have done. A simpler case here. We have A, B, C variables. These are not variables, literals. These are my terminal symbols. And is this actually, what can we say about this one? Now, let's take a simple case where we have this A plus B times C, right? Using this grammar. Can this grammar explain this or parse this? Yes, it can parse it. And there are two possible parsing of this thing. I'm not going to say that LR or LL will do this one. In general, I can easily see that if I call this, if I rename this E as an expression as an E, I have E goes to E plus E. So, and then I would actually go and do this one first. Whereas the other one actually says E goes to E plus E times C, and I'm doing actually this one. Okay. Now, these two trees, these two parse trees are actually completely different. You can see them, right? They are kind of, they look like shape-wise mirrored or something like that, but they are different. They are different parse trees. Now, usually what happens is that, or not usually, what we do is these parse trees, if we have two different parse trees for a given input, this means that this explanation that we have for this input is not unique. We have two explanations. We can describe in two different ways. We can describe it in two different ways, right? Now, so what does this mean? This means that if I actually, so these two parse trees, when I put a meaning, now this is the concrete syntax. Right now, what I'm trying to do is I'm trying to look at the concrete syntax, meaning, is this a part of my language? Yes, it is a part of my language. This is a valid expression. But there are two ways that I can actually interpret this as a valid expression. Now, the question is, when we look at the abstract syntax, meaning the semantics, what am I going to do with the semantics? How am I going to interpret the semantics here? This is the abstract part of the syntax. And what we usually do is to make our lives easier in compiler design. We want to actually use this parse tree to also associate the meaning, the underlying meaning, not just the concrete syntax, but the abstract syntax can be kind of extracted or can be applied or can be, let's say, interpreted using the parse tree. How? For example, if you are able to just, an expression should be generating a value, right? Okay, so how would you actually generate a value here using this one of these expression parse trees? You say, okay, what is my value for C? Let's say that this is 10. I have, we are going to see this one later on. We are going to call this some sort of a augmented grammars. Now, I can actually say if this is 10 and if this is 5, if B is 5 and A is 2, I can already see that I can use this part of the tree to bottom up to find out, first of all, what E is gonna be. E is gonna be 5 because E means expression. If I have expression equals A, I can write a rule saying that just pass the value of A to the expression, meaning now this is 5. Now this is, what did you say, 10. Now, what about this guy here? This is E times E. So one of them is 5, the other one is 10. 5 times 10 is 50. So now I have the 50 value here. And then 2 plus 50 is 52. This is nice. This is one value. If I apply the same algorithm, the same augmented grammar, here, this was 2, this was 5, and this was 10. This is going to be 10. Plus 2 is going to be 7. 7 times 10 is going to be 70. Now you can see that the associated parse tree can be easily used to actually get the semantic, the meaning of that expression. And this is very useful. I do one thing and I have an answer for two things. Both concrete syntax I have an answer for. Yes, this is a valid instance of my syntax, or no, it's not valid of my valid syntax, or valid syntax like this. And then the second thing is that once I actually answer that question, I have a derivation tree, a parse tree, and this parse tree can be used to actually associate the meaning easily without any difficulty, very, very easily. But if I assume this is the case, and if I have two different parse trees for the same input, then I have a problem. I have an ambiguity in my meaning. If I interpret it one way, I will get 52. If I interpret it other way, if I parse it the other way, my tree, my input, it will get 70. Now I have a problem. If you recall, we said a programming language should generate, an instance of a programming language should generate the same input, same output for the same set of inputs. Here, I'm not saying that. I'm saying that, oh, in one case, I'm going to tell you 52. The other time, I'm going to tell you 70. Where did this come from? This come from the fact that my BNF, my grammar, is actually ambiguous. And how did I find it? I found it simply, one way of doing it is actually, maybe it's not sufficient, but one way is I derive my grammar leftmost first. This is a leftmost derivation. And then I do a rightmost derivation. No, actually the other way around. Anyway, so, and I ended up with two different parse trees. So we call this a syntactic ambiguity. This syntactic ambiguity actually is not a big problem right now when I actually just look at the syntax, the concrete syntax. But when I look at the semantic, this is going to be a big issue for me. The way that I am actually kind of, let's say, putting a meaning to these expression, these rules, the BNFs, the production rules, they are going to actually give me several different meanings, or in this case, two different meanings. Therefore, this ambiguity has to be actually, you have to be very, very careful when you define these type of things. The ambiguity is not there, because if the ambiguity is there, you have to actually make sure that you catch it, and then you have to make sure that you handle it somehow. You have to say something about this. Either you make sure that your grammar doesn't have it, description of your or specific grammar that you actually described doesn't have that syntactic ambiguity, or if you do have it, hopefully you shouldn't have it, because then you have to actually have exceptions in your communication to define what things are, or and how they are handled. And this is kind of very difficult to avoid. Why? Because this non-ambiguous, unambiguous grammars, these, let's say, languages using these type of context-free grammars, they are not very expressive. You have limitations in them. When you have expressiveness, you have to actually, you are start going into these, or you tend to introduce these ambiguities. And sometimes you may not have any other choice. It may not be as simple to actually just remove as an ambiguity of this sort by changing your rules and whatever. Okay, and then when you don't have the this or when you have these type of ambiguities, you have to have some explanations as to how you resolve them. And there are quite a few very well-known examples of this one. For example, this, let me see. No, I'm going to come back to that later on, I guess. Let me actually go. No, apparently it is not here. So, for example, maybe it is somewhere here. Okay, anyway, like this well-known dangling else for an if statement. This dangling else, the kind of the ambiguity where your else statement, which part of that else statement actually belongs to in the if, which part of the if you have nested ifs. In these type of things, these are inevitable. And maybe making them disappear might actually constrain your language quite a bit. And you know that for example, for C, dangling else can be easily resolved if you always use curly braces. But you don't use them. Why? Because it provides you some flexibility, at least in writing. And when you do that, if you're forced to use them, you get that flexibility out of the way, or get that flexibility out of your language. And maybe sometimes it is easy, or maybe it is justified. Sometimes it may not be justified. It may be difficult to actually justify because, for example, for C, even having two braces, curly braces, might make your code, let's say, look too, let's say, cluttered, or maybe too many characters in the source code, which may not be what, let's say, your language's intent is, which was the case for C anyway. All right. So any questions? We are going to continue with this LL and LR algorithms, how they are implemented, especially the LR algorithm. We are going to focus on that on Wednesday. And we'll touch up on that syntactic ambiguity again after we discuss the LR algorithm, because you are going to see where it appears in that algorithm easily. And hopefully we'll conclude this thing next Monday, this section of the course next Monday. Any questions?
Hocam, next homework will be about Lisp or another main?
It's gonna be, I think, if we are, let's put it this way. Most probably it's gonna be in C++, asking you to implement a lecture. Most probably. But we are gonna decide it later today, and it may be also a lecture in Lisp as well. I don't know yet. But it's gonna be a lecture. The problem is gonna be a lecture. Do we do it in Lisp or do we do it in C or C++? We don't know yet. So in a few days, hopefully. Any other non-homework related questions?
Sure. What are we going to do in Wednesday?
On Wednesday, we are gonna continue with the LR algorithm. This, what we call this shift reduce parser.
You said next Monday, so that's why I am asking.
We are gonna no shift reduce parser next this Wednesday, and we are gonna conclude this grammar topic on Monday. So this chapter, syntax analysis, will be concluded on Monday, hopefully. Maybe just a few things might remain, but I'm trying to finish it up by Monday. At the end of Monday, we should be finishing this topic. So shift reduce parsers, and then wrapping up the topic of syntax analysis on Monday. Shift reduce parser on Wednesday. All right. If there are no other questions, I will stop recording. I wish you all a nice day.